Alright, so in this video we're going to be learning about higher order derivatives. That is, how do we take the derivative past the first derivative? So moving on to things like the second derivative, third derivative, and so on. So this isn't something that's going to be necessarily more complicated than what we've been doing so far, just a couple more additional steps. But primarily what we'll be using a lot in later concepts is going to be things like the second derivative. But past that, things like the third, fourth, fifth are often less common. So, but just know how to denote this in terms of symbolically, in terms of notation, as well as how to approach a problem where, in case they do ask for higher derivatives. So we'll begin by looking at the notation. We know that we can denote the first derivative in a number of ways, one of which includes writing it as y prime. We can also say f prime of x, for example. Here, let me write this with some more room. So we can say something like y, it seems to be glitching. Sorry. Alright, let's see if I can make it stop glitching. Alright, so we know we can denote the first derivative as y prime. We can also say f prime of x. This is another acceptable notation. And similarly, we can also say, if we're using Leibniz notation, we can say dy dx. dy dx. So these are all things that we've seen so far. Now, what about if we want to take the second derivative? We denote the second derivative in a very similar fashion to these. We can do it again in three ways. We can write it as y prime prime, two primes, right? Second derivative. Again, f double prime of x. Or we can write it, if we're using Leibniz notation, as d squared y of dx squared. d squared y dx squared. Now, the third derivative, as you may guess, we can denote it as y prime 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 f prime 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 of x, and here this would just be d cubed y dx cubed. Now, if for whatever reason we need to start taking even higher order derivatives, like the 12th derivative, for example, you can see how maybe writing like 12 primes could become very tedious. So, and instead of doing that, we can simply write it as y to the, in parentheses, whatever derivative that is. So y, this is referring to the 12th derivative. Same concept over here, where we would write f to the power of 12 of x. Or again, over here, it just would be whatever value here. This is d to the 12th y dx to the 12th. So if we wanted to write this in a more general form, the way that we write any of these would simply be y to the n, f to the n of x, or d to the n y over dx to the n. So this is the way that you would, denote higher order derivatives. All right, so now let's look at an example of how we approach a problem. So let's say that we're given a polynomial function, and let's see if you can find the first derivative, second derivative, and so on. All right, so if we're given some function f of x, f of x, let's see, hopefully this is within the frame of the video, yeah, f of x is equal to x to the fifth minus 2x to the third, that's a 3 third, plus 4x squared minus 3x plus 6. We're given this polynomial function here. What would be the first derivative? Well, we can write our f prime of x. We're using this notation here. So f prime of x. Let's just take the first derivative. That's easy, right? This would be 5x to the fourth minus 6x squared plus 8x minus 3. And again, the derivative of a constant is 0. So this would be our first derivative. Now the second derivative, all we have to do is take the derivative of the first derivative. It's as simple as that. So this would just become, the second derivative would simply be the derivative of this. So that would be 20x cubed minus 12x plus 8. And you'll notice again, then if we go on to take the third derivative of this function, this would become 60x squared minus 12. And so going on, so on and so forth, you can see that eventually, if we continue taking the derivative of a polynomial function, it will eventually reach a point where it becomes 0, because we'll end up just taking the derivative of a constant, which would end up being 0. And no, again, this is only the case for a polynomial function. It's not the case for all functions, where if you continue taking higher order derivatives, you eventually reach 0. It's just for a polynomial function. We know that, as you can see, we continually end up with smaller and smaller expressions until eventually we end up taking the derivative of a constant. So for a polynomial function, higher order derivatives eventually will lead to getting an answer of 0. So now, this is kind of just the way that you would approach taking a higher order derivative for any type of function. So if we wanted to find the second derivative, we would first proceed by finding the first derivative and then taking the derivative of that. So it isn't anything very complicated here. Now, what about when we were talking about implicit differentiation? If we were trying to do a second order derivative for with implicit differentiation, that's where things may get slightly more complicated. But again, nothing too crazy. So if you remember how we approached implicit differentiation in a previous video, um, it's very similar to that. Again, if you don't remember, be sure to check that video out. But in any case, if we're trying to find the second order derivative, let's say, um, I'll write it like this, f prime of x for our function sine of y, or sorry, we're trying to find the second derivative of a function sine, or of our equation here, sine of y is equal to x plus y. Again, we can clearly see that this is an implicit equation, as we can see that we are dealing with two different variables here in the same equation. So this is an implicit equation. So we start off, as with anything, as what we've seen at least, by finding the first derivative, and then of that we will take the derivative again. So the first derivative here, what do? Well, we approach it by saying the derivative would end up being cosine y, and again the derivative of y is just dy dx, because again this is chain rule. So cosine y times dy dx is equal to 1 plus dy dx. Now let's move all the terms with dy dx to the same side. So we get cosine y dy dx minus dy dx is equal to 1. Factoring out dy dx, we end up with dy dx times cosine y minus 1, and this is equal to 1. So then we get our dy dx to be equal to 1 over cosine y minus 1. So this is our first derivative here. Again, we can go on to rewrite this as cosine y minus 1 to the negative 1, because this is just the reciprocal. So now how do we find the second derivative? Let's just clear up some space here, and the second derivative is just going to be the derivative of our dy dx here. So to take the derivative of this isn't something that's too difficult, right? If you want to rewrite that in the form d squared y over dx squared, the second derivative is simply going to be equal to negative 1 times cosine y minus 1 to the negative 2. Now going inside, right, chain rule, we get derivative of cosine is negative sine y, and the derivative of y, we end up multiplying y, dy dx. So hopefully you can see where what we're going with this. Now, eventually, all we'll have to do is, we have this term here, dy dx, and we previously found what that is equal to when we found the first derivative. We saw that dy dx is simply cosine y minus 1 to the negative 1. So we would then substitute that, we'll just plug that into here for the second derivative. So then we would end up with our d squared y dx squared to be equal to negative 1 times cosine y minus 1 to the negative 2 times negative sine y times cosine y minus 1 to the negative 1. So now if we want to go on to simplify this, we can see that we get an answer. This becomes just negative 1 over cosine y minus 1 squared. And this would be on top, so we get sine y over cosine y minus 1 squared multiplied by 1 over cosine y minus 1. Applying a little simple arithmetic here, we get our answer to be sine y over cosine y minus 1 cubed. So this is going to be equal to our second derivative. Our d squared y over dx squared is going to be equal to sine y over cosine y minus 1 whole cubed. So this is how you would approach any implicit differentiation problem. You take the first derivative, eventually you reach a point where this dy dx term will reappear, and instead of leaving it as such, you would simply plug in the first derivative and continue evaluating this algebraically. So this is the only example we'll go over here in this video, again, just because it is a repetitive process. There isn't really much else to see here. As long as you know how to do implicit differentiation, how to find a first derivative, how to find a regular derivative, second and any other higher order derivatives is just a more tedious or repetitive repetition of that same process. So that brings us to the end of this video. Hopefully you found it useful. If you did, please show your support by liking and subscribing. Leave any questions you may have in the comments, and I'll see you in the next video.